Hello, everyone. Welcome to the next joint meeting of quantum computing meetups groups from Washington, Warsaw, Toronto, and Alexandria. My name is Pawel Gora. I'm a representative of Warsaw Quantum Computing Group, and I will be one of the co-moderators of this meetup. Second co-moderator is Hennking Dekant from Toronto Quantum Computing Group. And we also have Kareem El-Safty from Alexandria Quantum Computing Meetup. And today we'll host three great speakers. So in fact, two, because Dr. Bartan was not able to join us. The first speaker is Aroosa Ijaz, and the second is Dr. Brajesh Gupta, and he will cover also the part that was intended to be given by Dr. Bardan. So today the topic is quantum machine learning lightning talks, hybrid quantum classical algorithms in quantum machine learning, a lightning review. So before we start, we would like to also ask you to ask your questions or post your questions on our chat. After both talks, there will be Q&A sessions during which we will just try to ask your questions. And also, we would like to thank our sponsors, our co-organizers, Quantum AI Foundation, Warsaw Quantum Computing Meetup, Alexandria Quantum Computing Meetup, Quantum Computing and Data Science from Toronto, and Brooklyn Quantum Computing Meetup, Orion XNet as well, and Association Quantum, Q Mexico, who is also one of co-organizers of our meetups, and Q Egypt, who is also one of co-organizers of Alexandria Quantum Computing meetups. So I think we can start. So I will just stop sharing my slides. And yeah, Aroosa, the Zoom is yours, so we can start.
So I'm Aroosa. Thank you for having me, everybody. I'm a PhD student at Waterloo, and I've also worked in the past as a quantum machine learning scientist at Xanadu. So I've been sort of in this field for like a couple of years now, and not a lot of people talk about the theoretical foundations of what quantum machine learning does. And there are a lot of gaps and unknown things that are going on. So for example, you get a lot of questions about, if I'm using a quantum neural network, what kind should I use? What should be, like the number of qubits, or how many sample points do we need? These are all questions that are related to quantum learning. And this is a very young field, so these are all questions that we're hoping to answer in the future. But studying this theory of learning would help us answer them better. Okay, so the outline is that we will, because I don't know who's in the audience, so I always try to make my talks a bit fundamental, and I try to cover everything I can. So we'll talk about the basics of learning theory, and then we'll talk about a certain model of learning or a way of learning, which is called probably approximately correct learning, PAC model, and we'll see that in both classical and quantum setting. So let's do the basics first. Okay. So learning is essentially, how humans learn. We learn from our experiences, whatever happened in our life, or we see other people, and there's this collective knowledge that helps us correlate events and, ideas with each other. And we're able to learn and make sort of belief systems about things around us. So this is, something we want to hand over to machines in certain cases where it's hard for humans to, like make quantitative rules about learning. And we want machines to sort of be able to make correlations or functions and to be able to see pattern in data for learning purposes. So this, the computational learning theory is basically the fundamental like paradigm where you formalize this and you say, okay, what can I learn? What can a machine learn? And if I can learn a task, how many data points do we need? What kind of data do I need? And how much time would that take? So these are two like different, two criteria of looking at it. So there could be sample complexity that we look at for a task, which basically is, how much data do I need, and the amount of time is called the computational complexity. And so, yeah, in the end, we want to have like a paradigm or some kind of like structured models that help us guess, okay, with this much certainty, you'll be able to learn. So what are like, our confidence tolerances or confidence intervals? So this is sort of all comes into computational learning theory. So I came across this really nice paper. It's an experimental paper and it's not related to machine learning, but I thought it was a very nice example to motivate learning example. So in this paper, what they do is essentially study aging. And aging is, longevity and aging is a big topic in research right now. Because, in medicine and humans want to see if we can live longer and be healthier. So we try to isolate different factors that affect aging. And one of the factors could be diet. So in the study, they, for example, look at mice of different strains and gender. And they sort of have these two cohorts. And one is fed a low or chow diet, low fat diet, and one is fed a high fat diet. So HFD and CD are the abbreviations for that. And then they sort of look at, what happens to these mice over time. So there are some correlations that they're able to make. So for example, they look at how much weight is gained over, the age of the mouse for different diets. So you can see here that they sort of fix the parameter of gender. And here they're looking for, again, a fixed parameter of gender, how long did a certain strain or how long did a certain mouse survive. So I looked at it, it was just reading, it's very interesting. And I said, okay, let's not go and use the usual classification example. Let's just pick this really nice study. And let's say that we look at a study and we want to design a new experiment. We are applying to this lab, or we're part of this lab where they're doing these experiments, and we want to design a new one where we are given data from this experiment, and we want to be able to design the next cohort. So we want to pick mice that, we want to see what kind of diet they were fed and how well they did. So sort of, like get some information out of it. So we can like look at the data we got and see, how much was the weight gain. So in the previous graph, so it doesn't let me go back. Okay, I have to, I'm sorry, just a second. So the mouse doesn't let me go back and forth, it only goes forward. Okay, I'll have to be careful with this. So yeah, I have this data. I look at like what's the weight gain for mice that were fed low-fat diet over first, let's say 800 days of their life. And what's the corresponding weight gain for mice that were fed high-fat diet. And then look at the lifespan. So you can see that those with the high-fat diet were living approximately on average, they were living 80 or 70 to 80 days less than the other ones. So yeah, we just have this data and we want to sort of make this classification per task for us. And we want to feed, we have this thousands of mice data, and it's humanly not possible to figure out what exactly is the function in there. And also we want this function, this predictor that is able to tell us, given the weight gain and the lifespan, so how many days the mouse lived, given this data, these two features, humanly it's not possible to really, label this, that which diet was used. And I want a general predictor. So general here means that any mouse that I pick in the world, I should be able to, figure out that, okay, if this is its, feature data or feature, I hope you're familiar with that term. Then what is the, what's the classification label for this mouse? So this is essentially what we are doing in this learning paradigm. But the first guess you might think of is, okay, let's try every possible function. Every possible function in the world, we apply to this and see which works best, right? Which best fits the data. And that sounds crazy because that is very, very expensive to do. And there's also, which, sort of what the no free lunch theorem says, that you cannot just go crazy with your hypotheses. You kind of have to, think of this or sort of use your knowledge to make better guesses. So what we can do next is not just have every possible hypothesis in the world, but we can have classes of functions or a class of hypotheses. So we pick a family of functions that look similar, and sort of we have to use our own guessing. So for example, you can guess that, okay, maybe there could be a polynomial function here. So you could try classes of all polynomial functions. Or you could say, okay, maybe I can use this rectangle. So you can use classes of all rectangles that, are axes aligned like this. But yeah, all of these have their own issues, as you can see. So for example, with the rectangle, this one seems to be, doing not so well. So it's saying, okay, everything inside is high fat, everything outside would be low fat, and that you can see might give a very large generalization error or performance error. Essentially, this wouldn't do very well. We'll come to generalization error later on. So then, as humans, we sort of already have this knowledge that, we can put in. So we sort of can guess that maybe there is some linear classifier here, or, just a straight line. So we just choose a class of, just all possible straight lines. And then the one we, all the classes we pick, it could or could not have the target function. The target function is the actual true function that for all data works in our case. It's, it classifies everything nicely. And we don't know what it is, but we're trying to like select a class in which the functions come very close to its target function. So that's the idea. So this is based on human knowledge. This is something you input. This, is also sometimes called inductive bias. That is required to make things work and not go, insane, essentially. So that leads us to the pack model. So far, we can, sort of see what the ingredients are. Now we know that we have some space of data points. So this is called instance space. And instance space is essentially all mice in the world. And this is not just limited to our data sets, all possible mice that I want to, work on. So any mice I pick from like another country or another lab or anything, we should be, our function should be able to work on it. Then we have the label space. This is just some terminology I'm introducing so we can, get a little more formal. So label space is essentially the labels and the space. This could be in this case this is binary, it could be anything, it could be continuous. In our example we have a binary label space, and then we input the hypothesis class, which I label H here, and the other thing I have is the subset of data. It's a smaller chunk of the whole instance space that I'm putting in, and it's, let's say it has like m number of data points in it. So m is just some number that we can pick, and each of this has the feature information. So in our case, the feature is the weight gain and the lifespan, right? So each data point gives me the full feature information and the label. So I'm given this labeled data that I give to the learner as input, and what I want from the learner is to produce, learner essentially is an algorithm, right? I wanted to output a function. I input a function. I wanted to give me a function that works well and it's close to the target function. So how do we know that it's close to the target function? We actually also don't know the target function. We'll come to that later. But yeah, so how do we quantify these things and say, okay, a learner is, how do we tell that a learner is good and a learner is bad? So we can go a bit deeper into this. Let me mention again. So there are some missing pieces. The other ingredients that we looked at, they sort of are, there's some missing pieces there. We don't know the actual target function. So essentially what we want is like, we want to make our algorithm to give a hypothesis that's close to it and can give me some kind of guarantee that it's close to it, but I actually don't know. So we'll come to this problem. And we also don't know the underlying probability distribution of the data. Okay. So let's just like go a little bit into what the error measures are. So let's say that we know the target function. Yeah. Then the generalization error is essentially the probability that the output hypothesis, so H that comes out, it's basically the probability that the learner makes error on any example it sees. So I pick any X from the instance space, and the generalization error is also called the risk. It's also called the true error. This is the probability that I make an error on any instance I see. Yeah, and this is something that I want to reduce, right? I want to have a learner that learns well and has a small generalization error. So it's usually labeled with L subscript F. So F here is the target function. So this sort of labels, that this is a true error. Some also notations include D here because D is the distribution with which the data is formed. So yeah, there are different notations used here. So these are the references that I followed for notation and also for the concepts if you want to look into it later on. Okay, so the other thing, the other thing is the empirical error. So I essentially, firstly, I cannot access the whole universe. I cannot access every possible rat in the universe. So the instance space is huge. So we cannot train on all of instance space, right? What we do, as I said, was take a subset of it and train our learner on that. And that is what we call the training error, empirical error. These are all the mistakes that our learner makes on the training data set. So the probability that h of x is not equal to f of x, so this is error, such that x comes from the sample of data points S. If there are any questions regarding the notation, you can ask now because the rest of the slides also have this. I'll wait for, if there are any questions regarding notation. So here L has the subscript S, which shows that it's, with respect to the sample. Yeah.
Mm-hmm. I think everything is clear. So there are no questions on our chat.
Okay, if I also talk fast, let me know because when I get excited, I do that.
Well, is LS including LF or vice versa?
So usually your true error will be bounded by LS. They're not like equal to each other, but they are related or bounded by each other. And yeah, it's a good question.
Mm-hmm.
Okay. So then what's the best we can do? Because there are bound to be errors. We don't see all of universe. We don't see all of instance space. So what's the best we can do given that we use a subset of our data? So if you do like business with anybody, if you make any models, if you go to like a statistician or you go to a consultant in a bank or anybody or accountant, you ask them to do something and they'll ask you how much precision do you want, with how much confidence do you want this to work. So essentially then we can do that. We can say, okay, I want my learner to work at least with this accuracy, and I want to be this confident about this accuracy. So this is the next, best possible option. So what we do is we set two parameters. One is called the accuracy parameter, this epsilon, and this essentially bounds my probability now. The probability to make an error, the true error on, the instance space, I don't want it to be larger than epsilon. So if this holds, then I know that H is working approximately correct. It has, it's working within this accuracy parameter. If H was greater than epsilon, the true error was greater than epsilon, then I know that learner is failing for this particular H. Yeah. Okay. Then the second thing we can, as I said, was sort of have this confidence in parameter. So this is also like, you see a lot in statistical learning. And so essentially you're saying that I want my learner to work with this, the probability that it works is this. So what essentially that boils down to is that the sample that I picked from my instance space is actually, it's a representative sample. It's not, for example, remember that in the diagram, we had this rectangle. So if I just pick like sample points or data points around that, that was a very bad sample. It had all the high fat diet mice and none of the low fat diet mice. So that is a bad sample. It would sort of tell my learner that, okay, all the mice weigh this much and all the mice live this long. And there's, all the mice are essentially just being fed the high fat diet, which is not true. It's just you saw a bad sample. So the confidence is essentially saying that the probability of selecting a bad sample is small. How small is delta small? So we set this parameter. So now, given these, maybe I explain this too. So like I said, the probability, the bad sample means that my hypothesis thinks is good. So I don't actually see any empirical error in it. So I see all high fat mice and I predict them well. So my hypothesis is looking really good, but it's actually quite bad. So it's actually failing because the true error for this hypothesis is greater than epsilon. So these two events, when they happen together, the sample is bad, yeah? And that's the probability that we are setting to a small number. And that will happen if you're choosing with the IID distribution, essentially, and you're randomly choosing data points, then this wouldn't happen. Okay, so given these two parameters and a hypothesis class, so all of these inputs, given these things, this basically dictates how big the sample would be, right? If I want more accuracy, I need more samples. If I want, if there are larger number of functions in my class, I could get more errors. So essentially, the sample complexity that we talked about, or the dimension or the number of sample data points inside the sample S, is essentially dictated by these two things. So here M epsilon delta is just some function of epsilon delta. I'm not specifying what function it is. And here D is some parameter that tells me something about the hypothesis class. So it's usually the VC dimension, but we don't have to go into that. We can just think, okay, D is some kind of parameter that captures complexity or captures some behavioral properties of my hypothesis class. And yeah, that's about it. We don't have to go into the details of this for a general discussion. So then we can finally put all of these together and formalize the pack model. So given any hypothesis class we picked, the epsilon we picked and delta we picked, we can work out how many data points are required. So this would be given by this function, and that function depends on all of these three things. So this function gives me a number, and that's the number of data points I need to use. And if this function is polynomial, so it depends polynomially with regards to these parameters, then we can start talking about things again. Okay, this is good. We want a polynomial number of sample complexity or samples. We don't want it to blow up. If we want a slightly better accuracy, we don't want it to go exponentially crazy, right? So that first requirement. And then given this, we can say that if I choose this number of sample data points that are dictated by this function, given all this true, then my learner should be able to pick a hypothesis with the lower risk of what? Of epsilon, with the high probability of what? 1 minus delta. So this is essentially the pack model. It's just saying that for any input distribution D, for any target function F that we talked about before, and for any delta and epsilon and hypothesis class that you choose, the learner should be able to give you an idea of the true error, which we don't know, we don't have access to, but it gives you an idea of the true error if you choose this large enough sample. If you choose this proper number of sample points, you will be able to have this guarantee that you are not going above the risk. So if this is true, then we say that our hypothesis class H is pack learnable. And recall that we talked about the time or computational complexity as well. So it could be that you have polynomial number of samples, but it takes a long time to run. It's like some kind of algorithm that every step, has some number of steps and it takes a long time to run. So time is a separate sort of dimension that we have to look at. And if the time is also polynomial in these factors, then we say that the hypothesis class H is efficiently pack learnable. So yeah, these are kind of two things that we have to keep in mind. So any questions with regards to the pack model?
Aroosa, there's one question that was asked on the previous slide regarding the sample data. I heard that data can be biased. How to make sample data unbiased? So it's not exactly related to PAC learnable, but there was such a question on our chat.
So yeah, what you have to, so selecting data is, something that we do, and to avoid these problems of, what's essentially you're talking about is the delta parameter here. So you don't want a biased or non-representative sample. You want to pick randomly in from, so what they do in machine learning, for example, is you shuffle your data and then you pick randomly, right? With uniform distribution or something. So that's I think is what you could do to avoid any bias or selecting something that doesn't really make a good hypotheses. Okay, thanks. So yeah, if you want to go a little more into the theory of this, this pack model was first formalized by Valiant in 1984. It's a really nice paper if you want to have a read. Very nicely understandable. So yeah, now you can sort of see how all of this underlies machine learning. There also we talk about, a learner making an algorithm. We choose models, for example, neural networks or classifiers, or we want, a regression with some polynomial function classes. So all of these factors together that make a machine learning are really at the basics. They are coming from the pack model, but we have to we have to make some relaxations. Like the pack model in its own is not fully applicable because it's very hard to make something true or work for all possible input, distributions and all possible target functions. So that criteria for pack model or pack learning is very strict, right? It has to work for every possible target function. So yeah, so everything else builds on top of pack model, essentially is what I'm saying. So in machine learning, you will, for example, not not have the criteria of, you don't have just label data, but it could be distribution over the data as well and stuff like that. So yeah, just it's like a practical application of pack model. Okay, so we've sort of equipped ourselves with the classical pack model. So let's see what happens when the quantum regime. And I won't go into details of all the quantum basics that we need. I think it'll just suffice to know here, because I want to cover everybody in the audience. It just suffices to know about the superposition. So in quantum bits or in qubits, we essentially don't just live in the 0 and 1 bit. We have a probability distribution over it, essentially. So alpha fraction of the time, or alpha fraction dictates that, okay, the bit is in 0 and the beta factor dictates it will be in 1. So this is something that's very fundamental to quantum mechanics. And when we want to write the state of this is like a very general 1 qubit state. When we want to write, we can very nicely do in this basis, right? So this, we can just hot encode the 0 and 1, and then this becomes a 2-dimensional, very nice orthogonal basis. And we can just pick alpha and beta to sort of becomes a state or, the explicit state that represents our quantum state. And one interesting, the fundamental difference compared to classical bits is that alpha beta can be complex. So these are complex numbers, and there's a condition that they have to add to 1 because, as I said, this is a probability distribution. But yeah, we essentially just need to know that there's this superposition, as we call it, of states when we talk about qubits. And as we go to higher number of qubits, then your one-hot encoding this one-hot vectors become larger. So if you have 2 qubits, it could be in possibly, they both can be in the zero, it could be in 0, 0, 0, 1, 1, 0, 1, 1. So it leads to these 4 possible vectors that represent your space now. And you can sort of, write your 2 qubit state here like this. Okay. So this is very interesting, the superposition principle, right? It seems like it will change a lot for what we can do with the pack model. So here I sort of made an illustration. If we have a classical learner, here we see the classical bits that go 0 and 1, and it's just some learners has some like classical algorithm or learner inside, and we feed it the data that all the samples we had, and what it outputs is for all possible epsilon, delta, f, and d. We are able to output a hypothesis H such that the probability of the risk being more than epsilon is very small. And how small? We are 1 minus delta probability is like, with this confident. So if delta was like, let's say 5%, I'm 95% confident that given these inputs, if I use enough samples that are dictated from that polynomial function, so given enough samples, I would be able to find a hypothesis that has low risk with 95% probability. Okay, so it's the same thing. The output will be the same, right? We want a hypothesis to come out. And for the quantum learner now, it's not discrete 0, 1 digital bits, but we essentially have 2 knobs like alpha, beta that we saw in the last slide that we sort of tune to see, to tune the overall state of the qubit. And so that means that I can input data in superposition. And this is something that was already proposed like back in 1995 or something, what we can do here is essentially have a superposition over all data points in my sample and feed that into my quantum learner. So here D is the probability distribution of the data. So for a point X, I pick it up, I see what is the probability of this occurring. I do the square root because the square root is, it defines the probability amplitudes in quantum mechanics. And essentially with this weight or this probability, I have this particular instance, and I can also encode the label with it, right? So rather than having this, I can actually, for example, I could have 2 qubits. One could represent the data and one could represent the label. And so I could just feed in all of the information I want just at once into my quantum learner. So that's the idea. But it's still an open, let's see how it helps or not, if it actually gives us benefit or not. Maybe I make a comment here as well that making this state is also expensive. So essentially, you are going over all possible data points and making the superposition, which requires a lot of qubits. And every time, the quantum learner is trying to learn something and makes a measurement, it'll just destroy the superposition, measure one data point, one x and f of x, and then essentially we wouldn't be able to access the information, right? So when we want to see the output hypothesis, we're essentially making measurements. And although the learner gets all of this together, so it's able to process all of this together, but we can only access one part of it at a time, right? Just as we have in quantum mechanics, you collapse the wave vector, we cannot gain all the information of all the probability distribution. We can only gain a part of it. So we have to probably do it again and again. And although it's quantum data, it's very expensive to produce probably. So just like a side note. Okay. So if I have a pack, let's say I'm able to make this quantum data, the superposition, I have some process of doing it. Does that mean that my quantum learner is more powerful? Well, there has been a lot of work in this, but there has not been, let's say, a lot of promising results. So in terms of sample complexity, this has been shown like already, I think 20 years ago or so, that there's not really much difference when it comes to classical learner and quantum learner when you talk about sample complexity, because maybe it's because, you have to measure and see. Actually, at the end, the hypothesis can only see one data point at a time because of the measurements that we make on it. So not much there, but there is hope in terms of time complexity, because time complexity is where quantum computers are more powerful than classical computers. So if there's some, we're using some kind of function or we're solving a task that depends on something that is faster for quantum computers, for example, factoring. So we know the very famous Shor's algorithm. If we want to factor something, it's much faster on a quantum computer. So if we, for example, are working with some data that depends on that, and the learner is able to use and exploit that, then we can actually get speed ups here in terms of time. Okay, so, oh yeah, I already said that. So these are also, I put references at the bottom in case you want to look into it a little more. Let me know how much time I have. I'm almost finishing up.
We can continue. So in the meanwhile, there are 2 new questions, I guess, 2 or 3.
Okay.
So 3 questions.
Okay, I think we can take them at the end, or are they relevant?
So if you are just about to finish, then I think we can go on and ask at the end.
Yeah, I'm almost at the end.
Right. Yeah, let's continue.
Okay, thank you. So yeah, so quantum learners can be more powerful in certain cases, and this is something that a lot of people are working on. And okay, I can just skip that. So this is just with regards to BQB class. So this is, the task that quantum computers can do faster that I was talking about. Yeah. So the problem with the pack model when it comes to quantum pack model is that this restriction is very strict. Proving or finding a task for which a quantum learner can learn successfully for all possible target functions and all possible input distribution, this is really hard. It has not been shown to work in any case so far. So you can prove like sample complexity bounds and all that, but it's very hard to sort of make this useful, right? So we have to sort of build on top of the quantum pack model, just as we built on top of the classical one. This is a very, very strict learning paradigm. So what has been done recently, well, not recently, but what has been done to like sort of make it more applicable in, how we apply the theory to applications, is that we relax certain conditions in pack learning and see, okay, if this still work, can I still get some kind of guarantees? Can we still get some kind of bounds on my generalization error? Because that's what pack model gives you, right? It gives you sort of a guarantee that, okay, you give me this much data points, with this much guarantee, I give you a hypothesis. So here I have some examples, and there are a lot more examples in literature. I have some references in the end that you can have a look at. So I just mentioned a few here. So for example, let's pick the easiest one. So let's do the one-way functions. So remember we talked about factoring helping with the Shor's algorithm, you can actually help in reducing the time complexity. So there are, for example, in cryptography, there are a lot of techniques used that are based on factoring, and they're based on one-way functions. So essentially, we want a function that is easier to compute in one direction, but harder to compute in the other direction. Exactly how our the crypto system is working on all classical and internet and everything right now. And so, yeah, there is, if you work with this restricted class of functions, so this is restricting, I'm saying my target function looks a certain way. It's not for all possible target functions, but it looks only a certain way. Then with this restriction, in what is called discrete log the 3-log problem in cryptography. There was a very nice recent paper from IBM's team where they show that this actually is doable with a quantum learner with exponentially less time. Another example where you have like some sort of relaxation is uniform data distribution. So we said that we don't know how the data is distributed. You can pick data randomly, but we don't know how it's distributed originally. We don't see all of it. We can't really, it's a whole task on its own to learn the distribution over data. If you restrict only to data that are uniformly distributed, apparently there are a lot of tasks that become easier. There are a lot of examples in this regard. So I'm just mentioned one here. There's also the corresponding reference, and that is the DNF class. So this is essentially just a way of writing Boolean functions. And it's just learning how to write the Boolean function in this way is a hard task classically. And if you use quantum learner, it becomes a bit easier. So yeah, this is also with regards to time complexity. But there are also examples where you have better sampling complexity. For example, I think there was a paper in 2018 where they have uniform distribution and they look at Fourier sampling from Boolean class or Boolean functions, and that also has less sample complexity. So these are different criteria that you can check and see what helps you, right? There's another example, also a recent one, where now they are working here with generative modeling. So the first thing they took away was the label. So generative modeling is like essentially unsupervised learning, right? We don't have labels anymore. You essentially have just probability distributions, and you're trying to learn a generator that can mimic the original probability distribution, right? So for this task, so they were able to show, I think, either polynomial or exponential less samples, and they were only restricted to discrete distributions. So with these kind of restrictions, you're able to do a little more. But when you try to make these flexibilities, there is some down point to it as well. And the down point is that giving guarantees is much harder. So for example, as I said in the beginning, you have quantum neural networks, and they essentially are a function, or when we pick a quantum neural network, we're working with a certain set of functions or a set of circuits, maybe in this case, that becomes a hypothesis class, right? But to say confidently that this will work with these many number of data points, very hard to say right now. And that's like a big question as well, because we made a lot of assumptions and we made too many relaxations, and it's hard to study it. I know some people are working on studying it in this theoretical framework, but yeah, exactly, this theoretical study is missing, right? So that's why we are currently struggling with understanding what quantum neural networks, what their power is. So yeah, that's the last note I wanted to make. And these are some references. These two are really good books. These are sort of the basics of pack model, this one. And these are, I also included this this link to my notes. So I wrote some notes recently on this, exactly what I'm saying, but just maybe a little, nicely done. And I put them on my GitHub, but yeah, I'll also put them on archive if it helps somebody. But not very mathematical, very qualitative as well. If it helps you, you can have a look, but also there are a lot of really nice papers in quantum learning theory that you can have a look at. So yeah, with that, thank you very much for listening to me. I hope you were able to get some idea about, how data and learning is connected and what do we need to make a learner successful. So thank you. I'd be happy to take questions.
Great. Thank you very much, Aroosa. It was a very nice talk. So yeah, we have several questions on our chat. So first, let's maybe go back to slide 15, because there's a question about whether there's something about reinforcement learning. So it's a question from Said.
This one?
Yeah, I think so. So I'm not sure if Saif is with us. Maybe you can just ask your question, unmute yourself and ask your question. I can just read it. Do page or slide 15 talk about something like reinforcement learning? Is it possible in what about evaluating and measurement? Like breaking superposition, is it required for optimizing and feedback cycle? I don't think so, to be honest, but probably it's a general machine learning framework, let's say, right? So we have data, we have model that should be optimized, right?
Yeah,
That
so
should
there are
be
two
trained. So
questions. Are we asking one about reinforcement learning and one about measurements?
yeah,
You
so
like
I'm not sure.
ask
Probably it would
one
be
at a
best if
time?
yes,
Okay.
probably it would be best if say if Mustafa would just unmute himself and ask this question, because I'm also not sure if we understand correctly the intention.
Okay, maybe I can clear up so the pack model that we studied is of course we are doing it in a certain setting. This is batch learning. So batch learning is where we have the data and we can look at all the data at one point. It's not, for example, there are, cases where the data comes in one at a time in sequential data or in online learning. So this is batch learning. And the other thing we're looking at is supervised learning. So under these two, sort of under the umbrella of these two, we're studying path model. If you want to generalize that, that is, it's doable, and you can you essentially have to. There are other learning models that exist for that. So maybe I should have mentioned that this is only for supervised batch learning.
Okay.
That we usually use in machine learning is, essentially what we're doing.
Yeah.
Most of the time.
Fine for me.
And the second
Okay.
question was?
Yes, there is another question which seems to be quite interesting and good. It's a question from Shadab. What data size can be handled for this kind of models on quantum computers?
For quantum computers. So I think at the moment the best hardware we have, so we have noisy devices and we have noisy qubits and noisy gates, and experimental physicists are brilliant people. They're working on it very hard, and we're trying to reduce the errors within our gates and everything. So I think the best hardware right now in the world probably has maybe Google or IBM has 60 to 70 qubits, and you can apply hundreds of gates, like maybe 100, 150, 200 gates. And then after that, it becomes too noisy and you cannot really do much with your computation anymore. So you have to sort of squeeze whatever you want to do, or your computation, or you want to learn function or anything, you have to squeeze within this time period, after which it becomes useless. So I think with 60 qubits you could still you could do still 2 to the 60 amount of data points, right? Which is a lot. But they're not all usually used. You need, some for labels. You will also need some for reading out, and some ancilla qubits for other purposes. And if you're doing error correction, then you also need to reserve some qubits for that. So yeah, you can think of this in tens of qubits. And tens of qubits mean that you generally can do like thousands of data points, thousands to millions of data points. So it grows exponentially, right? So if you have 10 qubits, it has 2 to the 10 power. But if you only have like 15 qubits, just 5 more, you can already do 2 to the 15 number of data points.
Okay.
I have a small question or comment, not question. So would I be correct in saying that for PAC quantum learning, one would need a full fault tolerant quantum computer, or you would be able to do PAC learning in some capacity using the next devices?
So the good thing, one of the reasons why quantum machine learning seems very promising at the moment is that the data can handle noise, right? So if I move my data a bit up or down, it should still be able to help my learner put out a hypothesis of some kind, maybe with a little more error, but that's the idea, right? Like machine learning can handle noisy data. So that's the good part, that we can use these noisy quantum hardware.
Okay.
Yeah, the power is limited at the moment in applications as well.
There is the next question about sample complexity. There was a slide about it. It's a question from Amir. How come the sample complexity is similar since data can be passed in superposition?
Oh, okay, this one.
So I think there was another slide. Yes, the next slide probably. Yes, here. So here you have that in terms of sample complexity, quantum and classical learners perform similarly, and I think that there's a question to just explain it.
Yeah, it is due to measurements, because what is the learner doing? It's looking at every data point and seeing and picking a hypothesis and seeing what's the error on that data point for the hypothesis I've picked, right? And the quantum learner can do that in superposition. It has access to all data points, and it can look at the error for all data points given a hypothesis. But when it outputs a hypothesis and we access it, we measure. We cannot look at all this information. We have to make measurements when we deal with a quantum machine, right? So I think essentially that is the reason that we have to we have similar sample complexity, because we essentially are sort of looking at the same number of data points. It's just the quantum one needs to be done many times, or because of our limitation of measurement. So yeah, I think in the original, so if you look at this first paper here, they have very nice proofs, and they use they sort of look they analyze this using measurements like you have in quantum mechanics. So they essentially treat all of these as states. So every data point, and with the hypothesis that acts on it, now this is some state, that a quantum state, and all of these different qubits are existing with each other at the same point, right? At the same time. And how do you tell two states apart in quantum mechanics has its limitations. We can only distinguish two states if they're orthogonal, and the next best thing you could do could be, they're called pretty good measurements. So yeah, if you look at this paper, they go into really nice analogies or way of explaining this. It comes down to measurements essentially.
So just to add to what Aroosa just said, correct me if I'm wrong, Aroosa, that the sample complexity in the quantum and classical pack learners they perform similarly, because at the end, the scaling of error with the number of samples still dictated by the central limit theorem. And so in other words, to get to to satisfy an inequality with error less than epsilon, you would still need to draw as many samples in quantum as you are doing in classical to get a certain level of error. So this sample complexity has to do with the number of samples drawn from using a quantum or a classical pack learning model. So as far as the number of samples are being concerned, and drawing those samples is concerned, it's quite natural that the quantum and classical, pack learners will behave similarly. But that doesn't mean that the quantum doesn't have any advantage. Like in the next point, Aroosa points out that in terms of time complexity, that is, to do those things faster, quantum devices may be useful. Yeah. So I hope this just adds to the clarification.
Yeah, I think, that does, but I will add a bit more to it. So when you say that we have to draw the same number of samples, now this is a bit interesting, because this number of samples don't only depend on epsilon and delta, but they also depend on the hypothesis class. Yeah. And the hypothesis class could look different in the two cases. So it's possible that the functions look very different for the two tasks or to the two learners. But yeah, I think in general, in the literature that I've read, I'm no expert in this, it seems that this only makes a constant factor difference.
Right. Yeah. So the scaling of the error with the number of samples still remains same, because that comes from the central limit theorem. That is the holy grail of sampling. So
I would also add, in a very simple terms, is that just because you have more number of data points, it does not translate to better accuracy or better outcome.
Yeah, it doesn't. It also depends on what you're trying to learn and how many functions you have in the hypothesis class as well, right? Like if you are trying to learn something very, very complex, but you don't have enough armor, you won't be able to, you essentially end up with a big error, even if you use large number of sample points.
Okay, on this capital D in this slide, the distribution that you assign to data, how actually you do it? You get a bunch of data and you assume that they distribute in certain way. That's your model. And then you play with different forms of the distribution function?
No, so the data is generated from some distribution. It's not changed.
Unknown,
it's underlying.
But the distribution is unknown.
Okay. No, distributions are not known. Distributions are not known. So the studies I mentioned in the end, they sort of relaxed this condition, and they took data that had a certain kind of distribution. For example, discrete distributions or uniform distribution, but they made this choice which kicks them out of the PAC model, because PAC model should work for any input distribution on the data. We don't know what it is, but because the idea is that you can't know this distribution until you saw all the universe of data points, right? You cannot be sure unless you see everything. And so we make this assumption in PAG model that the data points are IID, so they're identically distributed and they all have the same underlying distribution. So if I pick two data points from this universe, they have the same distribution, probability distribution. So they're essentially independent, and there are no conflicts there. And because of this IID, and assuming that we don't know this distribution over the universe, when we take a subset from this universe, that also will have the same distribution, right? It'll have the same underlying one and also IID data points. And that's why PAC model is like powerful, and it makes this very strict sort of a condition, which we don't have access to, and we sometimes relax, or not sometimes actually, we relax it to sometimes fit our tasks.
That's great. And for my education, what is PAC standing for?
It stands for this huge word, probably approximately correct. So probably with high probability, approximately correct, because it cannot be 100% correct, because we can never see all of the universe points. So it's approximately correct because we have confidence with this, probability. We're confident that it's approximately close to the target function.
So do we need to now learn approximation theory to understand what that means now?
No, well, it already takes into account that, right? Because when we look at errors, we are looking at our approximations. So the statistics is already built into it, right?
Are there examples for this PAC?
Of a strict PAC model?
Yeah, like for me, it's like 3 letters.
Yeah.
But I don't know what exactly it means.
It just means that it's just a guarantee. It's just a way of learning that guarantees that your learner is successful. And all it's saying is that because we cannot let's not just run around randomly. Let's fix some precision and accuracy and confidence. And then given that, this is the number of samples I need to give you a low risk hypothesis. That's just all it's saying. It's just a set of commands and algorithm that says, okay, pick this and this and this, and then your learner is working successfully.
Yeah, I mean, just to clarify a little bit, maybe this helps, maybe this doesn't. As Aroosa explained, there are like two levels of uncertainty, quote unquote. There is one that is characterized by epsilon, that is the error, and delta is the approximation. So yeah, it's like saying that a knowledge about something is dictated by two kinds of errors. One is that we know approximately what the answer is. And then we say this approximation has certain probability, 80% of probability being correct. Right? So there are two levels of errors here. And that's why the probability, the first term P denotes or dictates that there is some uncertainty in what we are going to predict, or what you're going to say. And the second term, approximation, says that what we are going to say is not a definite statement. It's an approximation.
Yeah.
Okay. So I hope that clarifies the meaning of PAC models.
Yeah, it helps. Thank you.
Thank you. Any other questions? I don't know when should Brajesh start?
Yeah.
I think there's one important question that hasn't been addressed yet in the chat, and that's about the discrete logarithm problem paper that came out of IBM research recently. And it made quite a bit of headlines, obviously, because the claim here was that for the first time you can show exponential speed up when it comes to quantum machine learning. And the observation that Amir made in the chat, I think, is pretty astute. Basically, he's asking, well, isn't it a bit contrived? Because we already knew that the DLP problem is amenable to quantum speed up. And so basically, they just constructed this problem to be mapped onto DLP. And I think that's a very, very good observation. And I just would like to expand on it a little bit, because they also said basically we have problems that are intractable for classical machine learning. So basically, I think that the claim that kind of gets overlooked in this paper as well is that, well, we say here that there are problems that no classical machine learning algorithm can really learn efficiently, and quantum machine learning can. So I think hidden in this paper is also the claim that there are problems out there that only quantum machine learning can solve. So I would like to just hear your thoughts on that.
Yeah, again, so when we talk about efficiency, we have to take into or think about, is it with regards to the sample one, or is it regards to the time complexity? When, for example, if you look at the quantum principal component analysis, or all this, or clustering, or these algorithms that sort of built on top of the quantum Fourier transform speed up. So if you do Fourier transform with a quantum computer, it has some speed up, and you can build on top of that and exploit that when you are trying to learn something. For example, in the QPCA paper, and they claim this again, exponential speed up, but speed up with regards to time, and also under under certain conditions that we have the ability to do quantum Fourier transform. And you said here, this example is a bit contrived. Yes, it is known that the DLP is is building on top of the Shor's algorithm. And I think what was nice about the paper was that they were able to show this, have evidence for this, and show this for a small device. And and also we're able to see these like maybe bounds or give guarantees that this is going to work. So yeah, it's theoretically known, but you always have to do the experiment as well, right? And they but added the sort of on top of the Shor's algorithm and this one-way function, they added this this idea of learning from data and being able to embed data into a quantum computer in a certain way, and they were able to successfully do that. So it's a good a significant step for the community, and yeah.
So what do you make of the fact that they basically say that the input data here that they constructed would just look like random noise to a classical algorithm? So a classical algorithm couldn't actually pick out that pattern.
Well, so for the case of DLP, it's if you're talking about generally you have random distributions, it's harder. It's very hard for a classical computer to learn that. But when we talk about it, this area is like it's ongoing research as well. What exactly characterizes what exactly differentiates classical and quantum boundary? Because even there was a recent paper from Caltech and Google collaboration where they show that even for quantum data, because we initially thought that if you have quantum data and you have a quantum computer that does machine learning on it, it should have some, it should be able to read patterns that the classical computer cannot. But that's not true, because classical machine learning, that's what we study today as well. If we give it data, it's able to learn functions. So this is a very gray area right now. It's a hot topic of research. So I cannot specifically or say with 100% certainty that this is the task that separates classical machines and machine learning and the quantum one. And here exactly is where quantum advantage is coming in. There are cases where, it shows more, for example, when we sort of make this relaxed assumptions. But yeah, this is, I would say, still under research. So I cannot make that definite statement, or I would be a bit scared to say that, no, this is where classical machine learning can never learn. So computation and machine learning is different, right? A classical computer doing computation is different from a classical learner trying to learn from data. So that the learner has more power because it can see, it has a different task to do. Learning a problem and solving a problem are different. So maybe that's the issue.
Yeah, well, I think thanks, for delving into this a little bit, because I just thought it was an interesting claim that they kind of buried in the paper, and I kind of feel similar about it. All right, thank you.
Oh, thank you. Okay.
Thank you.
Should I stop sharing? Are there any more questions? Or?
So in fact, I can see some comments, and I'm not sure if the question from Shadab was already asked. There was a question, so I think that this is a follow-up regarding the question about the size of the data. Is there any QML classification example available with 1,000 of data points? I'm not sure if it has been.
This 1,000 data points and it works. The classification is.
Yeah, probably, or maybe Shadab is with us, and maybe he can just unmute himself and try to clarify.
Yes, I was searching for any of the examples where huge, multiple data points are being used for training a QML model. So even I was trying from my end, but the system is going it's taking very long to run, and still the execution is not getting completed. So I was just wondering if there's an example which I can take as a reference, because the number of samples which I am using, it is having thousands of samples in that data set. So that's becoming a blocker for me, actually.
Yeah, I think a lot of literature does take that into account. So for example, by using the density matrices. But yeah, maybe send me some, if you can message me on LinkedIn or something, I can send you proper references. But I think you can like do this in a clever way, and yeah, because you shouldn't like put all the data points in at the same time, probably maybe do like a smaller batch, and yeah.
Sure, Ruth, I will ping you on LinkedIn then. That
Okay.
would be super.
Sure.
Thanks for that.
Yeah, so there are some suggestions now to just move on to the next talk, because we also have a limit for reservation time.
Yeah, thank you. I did take a lot of time, but
yes, yeah, but it was very interesting, right? So there were so many questions.
Yeah,
so
thank you for listening, everybody.
so your talk was very interesting, and yeah, so maybe if there are some other questions to Aroosa, then maybe please ask your questions on chat, and Aroosa, you can also read the whole conversation on our chat and maybe also try to answer them. Okay. But now I think that it's better to just go to the next talk. So thank you very much again.